Hi all, welcome to the next lecture on graph series. So today we are going to talk about traversals. So there are different kinds of traversal for graphs. I'm going to take the depth first search for this lecture. So traversal depth first search. As the name suggests, DFS means you're going to dig deep into the graph. So if you take a note, so you could have already studied about tree DFS, but here it is different because there is no root node as in the case of trees, right? So you can start from any node and you can go, and there can be many possible DFS outcomes for a particular graph. It depends on the way that you have defined the adjacency matrix or the adjacency list. Let us go through the algorithm now. Yeah. So if you see this, the DFS, right? So let me go through the algorithm. So now the main aim for us is to visit every node in the graph. So that's it. Visit every vertex in the graph once. Okay. Now, so the global array, we have to assume that there is a global array visited 1 to n, so that we do not repeat the vertices that we have already visited once in the path, and then we don't go into an infinite loop. That is necessary. So we consider a visited array 1 to n. N is the number of number of vertices here. So in this case, there are 8, 1, 2, 3, 4, 5, 6, 7, 8 number of vertices. So n will be defined as 8. So there will be an array which can be accessed globally in the algorithm, which will contain the numbers from 1 to n. Now, initially initialized to 0 means that can be a boolean value whether we have visited this array or not. Sorry, visited this vertex or not. Okay, initially as 0. Now let us take any one vertex. So you can start from any one vertex v. So visited of v should be 1 because we are considering this, we are in that position. So now we are going to 1 and then we assume that we have visited this. Yes, we have visited this. Now we'll go to all the neighbors. Now going to the neighbors is where the DFS algorithm comes in. For each vertex w adjacent to v. So you are in 1 and then who are all adjacent to you, who are all your neighbors, take them, and for each of them what you do, you again call DFS. So now for each of the vertex adjacent to v, you go inside this condition where visited of w, whether the visited is false. Have you already visited that? No. If not, then call DFS. Again this goes for a recursive call. Again what happens? This goes here and then that visited will become 1, where we are checking here the neighboring visited was 0. After calling DFS itself it will become 1. Okay. Now it will go inside and its neighbors will be called 1 by 1, 1 by 1, 1 by 1. If we run this example with this algorithm, you will understand why this is named as depth first search. Okay, now after every recursive call is done, we end the DFS here. So now let us go through this example. Yes, let me go through this example. Now take the main consideration node as 1. I am calling DFS of 1 initially. Let the visited array be 0, zeros like this. Okay, so let the visited arrays be like this. I'll try the visited array here. Visited array will be 0, 0, 0, 0. 0, 0, 0 and 0, right, corresponding to 1, 2, 3, 4, 5, 6, 7 and 8. Visited array is like this for each of the nodes. Now we are going to 1. Now what we will do, we will make the visited array as 1. Now this will become 1. Visited will become 1 here, right? Next, what we have to do, for each vertex w adjacent to v. How many vertices are adjacent to this? So now we'll print the value also. If you need, you can print the value here. So the recursive call will print 1. Okay. Now, next we need to go to 2 and 3. So this is the adjacency list. So what are all the nodes adjacent to 1, right? So we go to 2 and 3. Now for each vertex, so I am going to take 2 as the next terminology. Now visited of 2 is 0. Yes, that is true. Now I'll call DFS of 2 again, right? So now DFS of 1 is calling, I'm writing here, DFS of 1 is calling DFS of 2 because we need to keep track of this to complete the algorithm, right? DFS of 1 is calling DFS of 2. Now if you go to 2, again this value will become 1. I'm just crossing it down and writing it here. This value will become 1 because visited of 2 should be 1. Next, its neighbors. We call them 1 by 1. 4 and 5 are its neighbors. Now let me call 4 next. Call, and DFS of 4 is 0, right? Let me call DFS of 4. Now again 4 goes in, so 2 will be printed here. 4 goes in, visited of 4 will become 1. Visited of 4 will become 1, and now we'll write 4 here. Okay. Next, 4 is adjacent 1D to 8. So there is only one possible case that I can consider here, D of 8. I'm going to call DFS of 8 because DFS visited array of 8 is 0 because we have not visited it. We have not printed the output here. It's not visited. So again I'll call DFS of 8. Now it will go inside. Now DFS of 8, that visited array will become 1, and now I'll print the value 8. Now 8 has 4 neighbors, but then 4 is already visited. So I can, again from 8 I can visit for each vertex 4, 5, 6 and 7. Now what will I do? Will I go to 4? No, because this condition will fail. Visited of 4 is already made 1, right? I'll skip that. Now let me go to 5. Now I'll call this DFS of 5. Right? Now I'll go to DFS of 5. Now 5 will be visited, right? 5 will be visited once. And then for each neighbors of 5. Now for each neighbors of 5, if you think, 5 has only 2 neighbors, 8 and 2. Let me take 8. If visited of 8 is 0, no, it has become 1. If visited of 2 is 0, no, it has become 1. Now we have to backtrack because of recursion. Now D of 5 we called, D of 8 we called. Now this will go back here, putting the recursion like this. Now 8 had 4 neighbors, 4, 5, 6 and 7. We already visited 4, we already visited 5. Now we have to consider 6 under this for loop, right? So here visited of 6 is equal to 0. Yes, the condition is true. Again go inside and I'll print 6. And then make the visited of 6 to be 1. Now if you consider 6, again the same case, 8 is also visited, 3 is also visited, right? No, we have not visited 3 yet. So considering the neighbors for 6, if you can consider, we have 8 and we have 3. Now going to, so now this one has called in itself D of 6. Now D of 6 cannot call D of 8 because 8 has 1. We have already visited 8, so now it will go to 3. Now D of 6 can call D of 3. Right? 6 can call 3. And then make the visited of 3 to be also 1. Right? Now what are the adjacent nodes to 3? It is either 6 or 1 or 7. Now 6 is visited, 1 is visited, yes, 6 is visited, 1 is visited according to the array, 7 is not visited. Now that's the only possible case. We go back 1, 7. Now the algorithm did not end here. You need to backtrace. Now this will backtrace to here. This will go back here, this will go back here, here. But the problem is the algorithm is finite because every visited value will become 1. So for each vertex, if it still considers, this condition keeps failing and at one point in time it comes out. So the number of nodes should be, the output printed should be the same number of vertices in the graph. 1, 2, 3, 4, 5, 6, 7, 8. This is the DFS value that we have. This is the DFS outcome. Depth first. So we are going 1, 2, 4, 8. You're going towards the depth instead of going for the breadth, which we'll cover in the next lecture. Breadth first search, right? So now coming to the analysis of this algorithm. Now you have to be sure, like since we are using recursion here and recursion is based on the number of vertices, right? So it's obviously going to be order of V with respect to recursion. I'm not writing it as order of V because we have considered it n everywhere. So I'll write it as order of n, where n is the number of vertices. But now I'm not writing directly because of the recursion. It's also due to the visited array that we need to keep. If this visited array was not there, then this condition won't be there and it will get into an infinite loop at one point in time. You can try without doing that. So this is represented for two reasons. One is for the recursion stack that the program keeps, and one is for the visited array, right? Time complexity changes with respect to adjacency matrix and adjacency list. As we have seen in the previous graph property definitions, adjacency matrix is an n cross n matrix. And here, for each vertex, right, for each vertex, you need to traverse the that particular vertex particular row, right? For each vertex, you need to travel the row. So, and anyways, you're going to visit all the vertices, so it's going to be n into n. So, for adjacency matrix, it's always without any confusion, it's going to be order of n squared, because we are going to visit each vertex, and for each vertex you need to see its adjacent vertices, right? Then adjacency list, when we are coming to adjacency list, there can be a space that is reduced here. So what we can say is time complexity here. Because of that space reduction, time is also reduced. I'll explain how. Because here for each vertex, right? For each vertex you're going to visit, you're not going to check all the edges. So for each vertex, if you go, you're going to check only the adjacent edges in it. So if you count everything, it's going to be the total number of edges in the graph. Order of E. But you need to think about this, where the maximum possible value of E can be, max of E we have defined already as n into n minus 1 by 2. So which in turn again turns out to be order of n squared, right? So you can define this as, in any case, this is going to be order of n squared, and this is going to have the order of n, where n is the number of vertices. So understand that adjacency list is order of E because you have, for every vertex, you're just going to traverse its neighbors, and you're going to make the visited area as 1. So then you will not, for every vertex, you're just going to visit the number of edges. So it's going to be order of E. But E in term is in order of n squared, so you can always write it as n squared. Thank you.